Okay, for the demonstration, we're going to go ahead, and what I have set up here is an incandescent bulb down below, and I have a fluorescent, an LED bulb above. So we're going to look now and see what the waveforms look like. So right now we have 120 volts. As you can see, I have it set up with a special system back there where I can take current. I do have it on 1 time, so when we look at current and we look at watts in the end, it's going to be the value. So let's go ahead and we'll start with the incandescent, which is a 40 watt. Okay, and I'll go ahead and zoom in, plus we're going to see the power factor, which will give us a good baseline for whatever the power factor is for the system before we look at the other one. Then we're going to talk about what true power factor is. So power factor 0.990, that's associated with the building, okay, because it's basically it's a resistive. I haven't measured the lumens. I may or may not do that later, but in any case, we're set up, and as you can see, wherever I have it, the waveform looks pretty much there. One bulb, about 0.3 amps. So let's go ahead and we're going to collect this data. I think. This out of the way. You can't see that, but you can on the video part. So peak of about 0.5 amps. Now, I do know that part is going to look relatively low on this one, but wait till we see it. And then we're going to do the LED bulb next, and then we're going to do both, so we see what the waveform looks like with one sitting on top of the other. I suppose I could have done this shorter, but why not? I'm just leaving all the defaults set up. I'm staying out of the picture too. I've got so many things running, and sometimes my the videos look like a badly dubbed movie. Okay. And let's go ahead and take a look so we can note certain things. And I'm not going to go over to the waveform portion. We're just going to look directly at the end results. Nice and clean. The 15-ish hertz, that always shows up on systems. I haven't set anything up there, so let's take a look and see where we are. So power factor 0.991. It's really low on everything, 0.3 current, and we'll take a look at a couple other things in a minute. Then there's harmonics. Let's see what the harmonics look like for the system. So there's a tiny bit of 5th and 7th in there, air conditioning and heating, heating. It's about minus something outside is running. A little bit of second harmonic, a little bit of 3rd, 5th, and 7th. So that's the level that exists. So now let's go ahead and we're going to do the same thing. We're going to look at the waveform first. Turn this one off. And this is going to be what an LED looks like. Now current's much lower, but we have some other things going on. Okay, you can see the waveform there. We are at a power factor of 0.87, and that's just the based on the RMS. Current is extremely low. You can see here the peak is about 0.15. It's hard to read because you can see the chopping of the waveform. Okay, that's the LED driver. Okay, that is going back, because I'm measuring neutral, that is going back on neutral. So we're going to go ahead and download that and see what that looks like. Then we'll take a short pause, and I'm going to run the same things again at the 10 times so we can see the actual values. I can figure out what the kilowatts are by going to the kilowatt analysis portion of the system, but we'll do the 10 times, so it'll be an exaggerated value. See, we can do an exact comparison of the two, because they're both going to show up as 0. Okay, this is telling me very, very low current. So 0.0 something. So yes, we've reduced the amount of current. We have altered the waveform significantly, which means I'm adding a lot of harmonics into the system. I don't know what those harmonics are. We've taken a look at fifth, we've taken a look at seventh. Now, what do they look like? And third, that exist in the system, which are relatively low. I mean, I'm aware of what happens, so we take care of our system. So here we go. 0.876, same voltage. Current is below the 0.0 digit, so same as the other. Total harmonic distortion current, 60%. So let's take a look. There's our current there. We have some more second, it's exaggerated a little bit more. We very definitely have third and ninth, but we also seem to have fifth and seventh and 11th and 13th. We have three-phase harmonics coming off of our driver. So that adds to whatever's in our system. Now when we go into larger systems, now this is a high-end bulb. I purchased the higher-end LED bulb that's supposed to be clean. And as you can see, it's not so much. So when we start dealing with this, it's going to be relatively low. Let's see if I can get, yeah, it's still below the 0. Okay, so now let's go ahead. While we're here, we're going to go ahead and take a look at the impact of both. So now we have a sine wave and we have this sitting on top. Let's go ahead and zoom in. See what the power factor looks like with a linear load and a nonlinear load sitting on top of it. Okay, so we're at 0.989. So we have two 40-watt systems in place. This is called 40 watt, but as you can see, it's not going to be 40 watts. It's going to be significantly lower. But you can see these little tabs on there. And you can see we're up to the higher current again because we have the other lamp on there. So we definitely have a current drop. Let's see what things look like with both 40-watt systems online. Again, it'll take just a minute. And then, as I said, I'm going to go to the 10 time, so it'll be the equivalent of having 10 of each bulb on the system. So the voltage doesn't change, but the load would. So I'm going to simulate by using the second point on that, which is 10 times the current. So we look and see if I had 10 bulbs here and 10 bulbs there, and we're going to run the same thing over again. Stick it out. It's going to be interesting. The main thing that we're looking at is what is the impact on the system when we do that, and then when we do the next part of of what we're talking about, I will show you what a fluorescent-based system, a large fluorescent-based system, looks like from about a 30,000 square foot facility that's well lit. Okay, so both on there. Now the side bands that are occurring here, down here, those pop up with the LED. Those have to do with the harmonic content. So we're at 0.991. Okay, so not too bad. We have high harmonics, about 6.6% current, and about actually really close to 1% in voltage. And you can see by adding the additional linear current, we've dropped down the nonlinear current by a fair amount, but it's still very present across the board on my current. And on voltage, a little bit more, but it's pretty much the same. So let me go ahead and we're going to set up the next one. I'm going to turn these off. And I'm going to move the current clamp over. Be careful here. So now everything is 10 times the value in current. voltage is the same. So it's going to alter our load a little bit. So it's going to simulate as if we have 10 and 10, and then when we do the rest of it, it will be the equivalent of, so 400 watts and 400 watts, and then a total of 800 watts. So let's go ahead and we're going to go again. Let's take a look at the baseline, because I see a little bit of something there, and then we'll start over. I just want to see what's floating there. This would be the load of the device. And we are pretty low, about 0.1 amp. Now that would be 0.01 amp in reality, because I'm 10 times, and a power factor about 0.645. So that's what that waveform looks like. We're not going to catch that. That is basically the circuit as we have set up. Okay? And there's some stuff riding in there, so that's going to be the rest of the system, and I can hear my AC system, or heating, turning off and on in here. So all of this goes back to a 200 amp panel and back. So let's go ahead and we're going to turn on our linear load first at 10 times. So this should be, 30 amps? Or 3 amps, I should say, something like that. Let's get it down here. So about 3 amps. So 3.2 amps, 0.997 power factor. So the linear load is not having a significant impact on power factor. It should actually be 1 if I was in a perfect system. I'm just into an outlet. Okay. Now on that outlet, I have some of our servers and some other stuff, and that's all feeding a little bit. That's that teeny little bit in there, plus our air conditioning systems all come off the same system. Now, unlike my old facility, I don't have 277 480 here. It's 120 240. Or 240. Okay, and we'll see what this looks like exaggerated, so we get at least an idea as if I was running 10 of these bulbs on what the watts would be. So this will give us a more direct comparison. But the key is still that, and when we go back in, I'm going to show you how we calculate true power factor. In which case, we'd be adding together those additional currents, so when I run this, my true power factor is lower. Now, I cannot fix that using capacitors and the like. I can only fix that. Here we go. I can only fix that by filtering. So we are at 400 watts, or 0.4 kilowatts. So exactly what the bulb calls. Okay, and 0.4 kVA, so everything's linear, about 3 amps. We've got some, so very, very low 5th and 7th, very, very low 3rd, 5th, and 7th, nothing else that's there. So let's go ahead now, and we are going to repeat our prior experiment, and we're going to add 10 LED bulbs in effect. Okay, now you can see this popping up a little bit, and we'll get it more into scope here. Okay, power factor, a little improved. Okay, but you can see these peaks are very defined, and that notching, that is what happens with an LED system. It's not a sine wave anymore. Instead, I have that. Its actual peak current is about 1.5 amps, where when I did the other one, it was about 4 amps. But it's going to tell me it's much, much lower than that, because when I do the RMS or true RMS of this waveform, it's going to show lower. So it's basically taken several amps, and whatever the lumens are here, it's definitely appears brighter, but that could also be because of the type of bulb I selected, which is called cool white. If I selected something that more represented the color spectrum of the incandescent, then they may be the same lumens. I was unsure. I've got to look it up for when we do the next step. So anyways, let's go ahead and grab this and see what we see. I always do these a minute long just so everybody goes, oh, a minute's so painful. It's not true. It's not that painful. Besides, it gives me a chance to have a little, coffee in my RDI cup. For those who haven't done so already, I'm doing that presentation tomorrow morning early, the first one of the Mobius WOW, and we're going to be looking at the, some of the ins and outs of attempting to calculate energy consumption through vibration. Now, we have actually solved that problem, and it's a little more complex than people think. So we're going to go ahead and present that complex solution at the Vibration Institute. But for tomorrow, we're going to show you some of the conclusions and give you an idea of how you can estimate your losses. And only be for one time RPM to start. So okay, so you can see those side peaks are up. That's a harmonic. That's part of that driving force. Let's go ahead and take a look. So we are still below 1/10 of a kilowatt. So that is where the savings aspect is brought into the picture, but we're measuring right at the bulb. Okay? So what is the impact of the overall harmonics? And what we found in the field is the harmonics that we're seeing as a direct result of that notching, when it feeds into neutral, will generally eat up a huge chunk of the savings you see in an LED system. So we need to consider that as we go forward. We got 61% total harmonic distortion. The phasers, here's voltage, still pretty nice. So it does a good job of maintaining voltage plus big load behind it. In this exact circuit, I don't have a lot. I unplugged everything in the classroom for this. But there's our, harmonic distortion again in current, which is relatively large, and it's not just a triplet harmonic. It's 3, 5, 7, 9, 11, and 13. And you know what? Let's go ahead and see if we can go out a little bit further here. And this is where we'll get the rest of it. So let's see if we can get to the 50th. Let's see if there's anything else sitting out there. Holy cow, look at that. So yeah, all that harmonic goes all the way out past what we expected, right? So I was expecting to see some third harmonic when I approached this, because that's what we were told. But it turns out it's completely inaccurate. It's not just third harmonic going into my neutral. It's all of the frequencies. So pretty nasty there. So let's go ahead and we're going to run the last one just as we did the first one. Turn this on, and there we are. So we have a much higher current and everything else. So we know we had 0.4, 400 kilowatts before. Let's take 400 watts, before. Let's see what we have now with the 10 of both. So yes, part of tomorrow is also going to be looking at the motion amplification aspect. Now I have done work, so when I'm looking at the comparison, I have done work comparing the two technologies and verifying what we were seeing in vibration versus motion amplification. There was a very, very distinct difference in what I'm showing tomorrow, partially because with the vibration aspect, we're looking beyond the structural, okay? And with the other, we're looking at structural with motion amplification. Knowing that difference is important if you are a vibration analyst or motion amplification person. There's always going to be a difference between different types of technologies. Could be measurement errors, could be angles, a lot of things can occur. So now we got it. And as you can see, those peaks get bigger and nastier. Let's let this finish up, and we will take a look at our stuff. So we're still showing 400 kilowatts. 400 watts, 0.997, so not a big deal there, at 3.5 amps. Frequency, now this is basically what's happening at line frequency. Let's take a look here. So voltage, as we said before, relatively smooth. Current waveform, when we do 10 of both, it drops down a little bit more. I believe we are at a total, and I'm looking across 51 orders right now, but it's most of the way out, even with the linear load on there. So as I build up the linear load, that sinks down. On the other hand, if I add more nonlinear loads, whether that be additional bulbs or three-phase systems, control systems, variable frequency drives and the like, that gets more exaggerated in those, because just like sound, harmonics add up through the whole system. So by the time, if I added in my fluorescent lighting system here, I have not gone over to LED at this point, but I'm running T5s. So if I take my T5s and I go back and I take my measurements, I'll have distortion from that, and then I add in LEDs, and in my whole system, that's going to create an even higher thing, but back at the panel, not right at the system. Okay? So we often see that in surveys where somebody will go in, they'll say, oh, you're going to save energy, da-da-da. Here you go. Oh, you don't need to filter anything. We're just going to put this in. We're going to run it. And look, right here at the circuit, right at the circuit that feeds that lighting system or whatever, we're not seeing a change. But you go back further to a panel that's feeding a group of these systems, then you see the harmonics come up. It's part of the thing that we deal with when we talk about harmonic surveys, is taking a look at the entire system. It's one of the reasons why MotorDoc came up with some of our monitoring systems specifically for keeping an eye on that, because we like to measure at incoming power and what's the overall effect of any changes we make. And as a direct result, we're finding energy losses in areas we didn't expect, like ground and neutral. I mean, that's been, well, I've been floored. We'll just put it that way. So with that, I'm going to stop this part here, or we're going to go on to the next part where I get to sit down and relax. We were building panels all day yesterday for monitoring systems, so my back is killing me, and we'll go from there. You know, age.